Algebra 2. We are going to do some exciting things today with angles. So I hope you're ready and excited. One of the great things about trig in Algebra 2 is that we get to break out of just being in a triangle. Triangles are still going to be extremely important, but we're going to begin to look at angles that are larger than 180 degrees and are actually placed in the coordinate plane. So we need to know a few things about those angles. And so you can see here, we have the coordinate plane, an x-axis and the y-axis. And we say that an angle in the coordinate plane is in standard position when it begins over here on the positive x-axis. Its vertex is at the origin, and it opens in a counterclockwise manner. So we call this the initial side. It opens this direction. You can tell that from the arrow right there. And then it has a terminal side, the ending side. So the beginning side, initial side, the ending side, the terminal side. And that vertex is at the origin. So we have both what we call a positive angle and a negative angle. This is an example of a positive angle in standard position. It is going to open counterclockwise. So you can see we've moved up there 120 degrees, so it's positive 120 degrees. Here is an angle that went clockwise. It went down instead of up. And so we designate that with a negative marking. So that negative or positive is really giving the direction of the angle. Okay, so those are two pieces to start with. So let's do a little sketching of angles here, okay? And we want to talk about what quadrant the angles terminate in. So if I'm going to look at 45 degrees, this right here is always 0 degrees, and we know straight up top is 90 degrees, and so 45 is going to be right in the middle. I'm going to place it there with an arrow, and then I'm going to draw the arrow of what direction, and you can draw that initial side there. And I would label that 45 degrees. What quadrant is that in? That is in quadrant 1. Remember that your quadrants start here, and it's actually that standard position of an angle that determines the order. They go counterclockwise. This is quadrant 2, quadrant 3, and quadrant 4, and we like those Roman numerals to designate that. So if I'm trying to decide what quadrant 160 degrees in, I need to know that straight up is 90 degrees. All the way over here would be 180 degrees, and so I'm going to use those as a frame of reference. 160 degrees is going to be closer to 180. In fact, it's going to be 20 degrees away from 180, and that 20 degrees actually will play an important role. It's called a reference angle, and it helps us know where that angle terminates. So here, this would be 160 degrees. That terminates in quadrant 2. Negative 150 degrees. I notice the negative, that means I'm going to start here in that standard position, but I'm going to be going down instead of up, and I'm going to be going back 150 degrees. That means that this over here would be negative 180. It will be 30 degrees away from that 180 there. So this would be negative 150. That is going to terminate in quadrant 3. All right, two more. 330. Well, if this is 90, this is 180. Add another 90. This would be 270. This would be all the way around at 360. So 330 is going to be somewhere right there. I'm going to designate that with that roundabout arrow. I do want you to be drawing where does it go around, where does it end, the direction of that angle. And that ends in quadrant 4. Well, what do we do with something like this, 530 degrees? Well, that is more than 360. So if I'm starting here and I'm going around, there's 360. I think I'll grab my calculator. And how much more than 530 is, or sorry, more than 360 is 530. I will subtract those. It's 170 degrees more. So I'm going to have to go around 360 plus another 170, and I'll be ending, like, that's not very straight, but you know what I mean, ending right there with about 10 degrees left. So this one also ends in quadrant 2. Now, in each of these, we can go back to that idea that I was mentioning before about a reference angle. A reference angle is just, it helps you locate that angle in relation to the horizontal axis. So right here we said, well, this was 160 degrees. That right there is 20 degrees. If 160 degrees is theta, the reference angle theta sub r would be 20 degrees because it is 20 degrees off that horizontal axis. Always compare to the horizontal, never the vertical. The reference angles are always the horizontal. So here I went back 150 degrees. I'm looking for what is that measure right there. That would be the reference angle, and that would be 30 degrees. It's not going to be negative 30 degrees. Reference angles are always positive. It is a distance. Always where the angle is to the horizontal, to the x-axis. So what would that measure be? Well, this one is 330, so I must need another 30 degrees to move that up to 360. And here we went 360 plus another 170. That would be a reference angle of 10 degrees. And here is our definition of a reference angle. The reference angle is the acute angle, meaning less than 90 degrees, between the terminal side where the angle ends and the x-axis, the horizontal axis. So always back to that horizontal. These reference angles are going to help us a little bit later on as we develop something called the unit circle and look at trig values. All right. So another definition we need to keep in mind here is that of coterminal angles. Two angles in standard position are coterminal if they have the same terminal side, meaning they end in the same quadrant at the exact same place, but they have a different number value. So here, let's draw 150 degrees. 150 degrees, I'm going to think, ooh, that's 30 degrees before 180. So there's the angle 150 degrees. Now, if I want to name 3 angles that are coterminal with that, let's start with just one. Well, what's another way that I could end at that same spot? I could go around once and then end at that exact same spot. That would be taking 150 degrees and adding 360 to that. I'm going to grab my calculator. 150 plus 360 is 510. Well, that would end at the same spot. But what if we went around that circle another time? What if I added 360? Ooh, 870 would also be coterminal with that. And I could just keep going. Notice here, I just add 360. Look at that. All of those coterminal angles, they are all 360 degrees apart from one another. All a different angle value and a different angle magnitude, we would say. But they all end in the same spot, so they're coterminal. We could also go backwards and look from here. Backwards, that would be another way to come up with a coterminal angle. That would be 150 minus 360. That would be 210. Negative 210, pardon me. And then you could keep going around again in the negative direction and find lots more. So how do you determine if two angles are coterminal? They are a multiple of 360 degrees apart from one another, ending in the same spot, different number of times around that coordinate plane. All right. Let's see if we can find the mystery angle here. Draw an angle in standard position that terminates in quadrant 2 and has a reference angle of 35. Well, the first thing we need to do is figure out which one is quadrant 2. Remember, we start counting here and go counterclockwise. This is 1. So this is quadrant 2. So I need my angle to end over here. And it has a reference angle of 35 degrees. So that means that my angle will end 35 degrees up from the horizontal. So I'm just going to, I don't know that that's completely accurate, but I'm going to call it that. And I will label this 35 degrees, and that's the beauty of a math diagram. Once you label it, it is. So I am looking for that angle. That's the one I want. What would the measure of that be? Well, all the way over here is 180 degrees, and I want to be 35 degrees prior to that. So I'd look at 180 minus 35, and that would be 145 degrees. So my angle here is 145 degrees. Okay, let's try a different one. Now I want an angle that terminates in quadrant 4, so I want to terminate down here, and goes through the point 5, negative 5. Well, I think I'll plot that point, 5, negative 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's the point 5, negative 5. My angle is going to go through that point. Remember, the vertex of the angles is always at the origin. So my angle is going to go through that point. Pretend that that actually goes through that point. So this is my angle. Well, the question is, what's the measure of that angle? Well, it sort of goes back to the idea that I could, to the horizontal, draw this triangle, and this has a length of 5, and this went down 5, so it actually has a length of 5. Notice it's a 45, 45. This is a 90 degree right here. 45, 45, 90 triangle. So this must be 45 degrees right there. Well, there are a couple of different ways I can find this angle, but I know all the way around would be 360, but I'm stopping 45 before that. So it would be 315 degrees. Now you could do the same thing. Well, if that's 45, this is 45, and 45 past 270, you can do that as well. Multiple ways to come up with that angle of 315 degrees. Okay. All right, we have just 2 more examples here. We're going to bring back our ideas of sine, cosine, and tangent by drawing an angle theta that goes through the point. Okay, let's look at 3, 4. We want to go through the point 3, 4. So I'll put some nice little tick marks. Now the angle will always go from the origin, so I'm going to draw that from the origin. And I'm looking for an angle theta. It's in standard position, so it will be right here. This is the angle. That's what I'm looking for, and I'm going to call that theta. Now, notice you can always take from that point and drop down to the horizontal, always to the x-axis, okay, and create a right triangle. This side is length 3. This side we went up 4 because of the point 3, 4, and hopefully you recognize that as a right triangle, 3, 4, 5. If not, you can use the Pythagorean theorem in there. So it's a 3, 4, 5 triangle Now notice that I have a theta in there. I can now find the sine of theta. The sine of this angle theta is opposite over hypotenuse, so 4 over 5. The cosine is the adjacent over hypotenuse, so 3 over 5. And the tangent, that would be opposite over adjacent. And so we have our 3 trig functions. Now let's see if we can do that with this other ordered pair. -5, 12. Well, -5, sometimes you can even just, I'm going to call that -5. And I'm going to go up 12. So let's call that point -5, 12. And I can draw the angle in there. And I will drop down. Now, this is a little bit of a tricky part if you're not in quadrant 1. This is actually theta. But this angle right here is our reference angle. And the sine and the cosine, the tangent of that reference angle are the same as the sine, cosine, tangent of this angle theta. So we're actually able to take the sine of an angle that's larger than 90 degrees. This is really new. Before, we were always bound within a right triangle, and it would be 2 acute angles. But this is theta sub r. We know that this side has a side length of 5. We went -5. Here's another difference. We're going to keep that negative. It tells us that we're in quadrant 2. That negative is not so much a measurement as a direction. And up 12. Okay. So hopefully you recognize that we have got a 5, 12, 13 Pythagorean triple here. If not, again, you can use that Pythagorean theorem. And now it's extremely important that that 5 had a negative, because that puts us in quadrant 2. If I want to look at the sine of theta, the sine would be opposite over hypotenuse, 12 over 13. The cosine is adjacent, -5 over the hypotenuse of 13. Extremely important to have that negative. And the tangent, opposite over adjacent, 12 over -5. So notice here, suddenly we have trig functions that can have negative ratios. And that's fine because we've broken out of quadrant 1. We are no longer bound by just right triangles. We are doing trig in a coordinate plane. Now, I want us to actually find that angle theta. So when we go to do that, first thing we want to do is make sure we're in the correct mode. Make sure you're in degree mode. Okay, now watch what happens. If I solve this for theta, I'm going to do the inverse sine of 12/13. I'm undoing the sine function with that inverse. Well, that is 67.38. Now, that should be slightly bothersome to you because 67.38 is in quadrant 1, and my angle is in quadrant 2. This is not the theta I want. That actually is the reference angle right there. Okay, so if you do the inverse sine to find it, you've got to actually take 180 degrees and subtract that angle, 67.38, to figure out that theta actually is 112.62. So there's a little work to be done because that's going to give you the reference angle. Now, let's just try this. We're done. We found it. It's 112.62. But maybe you want to do that, find it using the cosine. So if I do inverse cosine of -5/13, look, that actually gives me 112.62. So there was no work to be done with that. That just happens to be in the nature of the inverse cosine function and its domain and range. We don't have time to really get into that discussion. It's hard to do online. So if you're interested in that, maybe we'll have an open session. We can discuss why the cosine, inverse cosine gives you the actual angle, and the sine you had to do some work. But let's try the inverse tangent and see what happens. Inverse tangent is 12 over -5. Oh, look, it gave you a negative angle. So you've got to do some interpretation there and go, oh, well, in my picture, is it giving me theta or is it giving me a reference angle? It's giving me a reference angle, but I don't want it to be negative. I want it to be positive. And then back with the 180 minus that to get us to the 112. So in summary, when you go to find that angle, you can actually use either sine, cosine, or tangent. But you have to look at your diagram. Your diagram is very important so that you can interpret what angle you're actually being given by your calculator. Is it giving you the angle you're looking for? Is it giving you a reference angle with which you'll have to do some calculations to find that angle? You have to interpret it correctly. Okay? So, good luck. I'd love to hear your questions or talk through any of these with you. So email me, contact me, and looking forward to seeing your work. Thanks.